Hey everyone, Sanjay here for part 3 of my homework for submission for computational methods. So what they want us to do is implement a flash calculation to calculate the vapor and liquid compositions of a flash drum given a feed comprising of 10 moles of each methanol, ethanol, and water at a temperature midway between the dew and bubble temperatures and a pressure of 101,325 pascals. So real quick, before we get into the Python, which I know you're here for, let me check my audio real quick. Nice. Um, and I'm going to draw a quick picture. So imagine, um, sorry, give it a second to respond. Imagine you have a vessel, right? You have a feed coming in, a mixture of liquid and vapor, and then you have your vapor coming off the top, your liquid coming off the bottoms, and then you have your feed, right? So mainly there's a very important mass balance, right? Super easy mass balance. NV plus NL, right? And then from there, we can just use the same minimization procedures that we were using earlier, right? To find out the compositions. Um, and but we want to keep this mass balance in account, right? So that's like one of our quote unquote constraints. NF equals NV plus NL, right? And then this occurs at a certain temperature and pressure that we're going to find. And for us, NF equals 10. So, anyways, now for the Python, not OBS, not again, right? Um, so, so basically, we're going to write a function. We're going to call it flash. And so, according to the problem statement, we need to take in feed, right? 10 moles of each, and then bubble temperature, and pressure. So I'm gonna say temperature, pressure, and NF, right? And then how do I want to go about this? So the easiest way is just to say like um, NV. So we're gonna have to make a function, right? So I'm gonna make equation, and it's gonna be v, and we're gonna have it um, we're gonna have it return something. Um, and so this is what we want to minimize, and I'm pretty sure that what we're gonna minimize here is still Rayleigh's law, because if you go to our handy dandy drawing here, the flash calculation here is in vapor liquid equilibria. So YIP equals x x times p star, right? And so we want this. This is our big constraint. Yeah. So I'm just gonna copy. Not here. Where is it? Yeah. Also, I don't want this to print anymore because we fixed our issue. And while I'm on the subject, last video we I realized that when I was making this function, I kept it as dew point pressure. It should be dew point temperature. So I have it fixed now. Um, right? But now we have to actually do this. We have to find the x's and y's. We know the pressure, we know the temperature, right? So suppose V is our guess for the vapor mole fraction, right? That would mean that NV equals NF, the note times feed, the feed of each of the three components times V, the number of mole fractions in each component, right? And that would mean the amount of liquid is just the amount of feed, sorry, excuse me, minus the amount of vapor. And then the liquid mole fraction, so you have to remember NL is an array of the each amount of liquid. So if I take each amount of liquid, divide it by the total amount of liquid, I should get each liquid mole fraction, the same thing for our vapor. There you go. Um, I forgot to define this. No wonder it was being all, yeah. Okay. Um, so there we get our x and our y. We have our x, we have our temperature, uh, hmm, we have our activity matrix, we have our y, and then so let's keep going, right? Um, so uh, to find, um, so for that's our guess, but our actual, right, it's going to be NV times, NV equals NF times, and then it's going to be root, right? And so we're going to find the roots of our equation. So it's an equation, right? And then our guess, we don't even have to be as accurate as last time. Let's just guess um, zeros. So zeros. And then I want to make this um, apply to x. So why is there, do the parentheses not match here? Okay, yeah, I don't need this one, right? And so that's the NV, and the same thing, the NL, the real NL equals NF minus NV. Um, NL equals NF minus NVX, and then we can just copy these two things, right? And then let's return X, Y. And then, so we're done, right? And then, so our components, um, so our NF for this will equal our X because it's equal molar mixture times 30 because there's 30 total moles, and that would make 10 moles of each component. Our pressure is 101,325. We defined that earlier. And then our temperature. So we need the bubble point. Um, so I'm going to say the BPT and the, no, not Blaise-Pauli type, BPT equals, and it's going to be NR bubble point NRTL. And then what does bubble point NRTL take? We wrote that one. So it takes in X, which we have, um, and a pressure, which we have. And then what's with this? Why is it okay? And then the dew point temperature equals dew. Oh, because it's bubble point. Python knows all. Bubble point TNRTL. Dew point TNRTL X or Y. Sorry, no, but X. Yeah, P. Um, and then our temperature just simply equals NP dot mean of the bubble point temperature, dew point temperature, right? And then so we can go call this flash function, temperature, pressure, NF. Do you guys see any problems here? Can I just run this? What if I just run it? There's a mismatch in, where is it? Flash, TPF. Optimize between the output shape should be 3 So what line is it? Oh, here. But it's 3 comma 3. No, I don't know why I was doing it like this. I should just do np dot zeros like that. Because we don't want it to just be 3. Hmm. For a function. Oh, it's just np zeros. It's not doing anything. I need to call the function. There you go. Hmm. Oh, there shouldn't be an asterisk there. Dang, there's an error that I purposely included, but now I'm just getting errors. Um, shouldn't this shape just be dot x? Um, there's a mismatch between input and output type. I just want to make this apply to x. Should it be like this? I feel like that's wrong though. Here, let me pause the video and I'll get back to you. Hey guys, so I realized the problem. It's when the bubble point NRTL it gets returned, right? It's actually returning it's returning both of the what we ask it to do. So it was returning the compositions and the um the the temperature, but I just want the temperature, so I'm gonna subscript it um and into the bubble point temperature. I want it to be 0, right? Now, fingers crossed, I'm gonna print T. Okay, so we got that. Um, and now let's do the flash point. So let's say flash T, P, and F. See what happens. So we got a runtime warning, right? And why would we get that? I we had all of our constraints, or did we? So a big constraint for us is some of the mole fractions must equal 1. Now we can add that constraint or we can get rid of it. So in homework 3, I talked about a way to get rid of a constraint for the mole fraction equals 1. And here we can use the xbit function to basically apply the operation 1 over 1 plus e to the negative x to our um, uh, to our sorry, to our mole fractions, right? So where would we do that in this flash calculation? Very beginning, we want to say exp it, right? And then it's also going to be exp it here. And then those are the two places where we wanted to get rid of that constraint. And then look at that. So we run the flash calculation, and then we get the following splits for um, the vapor and the liquid. I believe, how did so I said that's a liquid mole fraction and then vapor mole fraction, right? And if I wanted, I could even find like the total in the vapor phase. So um, like this. Mm, why didn't you? Oh, I guess I would want the sum if I want the total. So I want sum of NL divided by or divided by NP dot sum N um, F. And you get 64% of your feed is in the vapor phase, or your of your products in the vapor phase. So I hope you guys enjoyed this video, and I hope you found it helpful. That's the end of my Homework 4 series. Thank you, and have a great day.